let's finally define, finally this is the last portion of section 1.2, defining our first actually useful sigma algebra. And this works, so in the textbook they do it for Rn specifically, but it's something that really works for any topological space. Now we haven't done general topology in the 118 series, but we can still do it for metric spaces. So I think your textbook is just not assuming that you want to work in that level of generality, or it's not assuming that you have a topology background necessarily, but we have a little bit with metric spaces. So let's do it for metric spaces. Let it be any metric space then in the context of a metric space we have a notion of which subsets are open. So typical example would be Rn, right? But also it could be a subset of Rn, right? Then it has a subspace kind of, in topology you call it the subspace or relative topology, and there's a particular notion of what are the open sets of the subspace. Okay, so that's coming up in a moment. So X, any metric space. Then let's also define, to make this easier, let's call it tau, or script t. Let's try this for script t. I don't like that. I don't like that either. Okay, I got it. This is my script t. So let this be, I haven't made one of those for a while, the collection, the set of open subsets of X. Okay, then, so I'm about to give you a definition, but before I give you the definition, let me remind you exactly what I mean by this in this context. So here I am in good old Rudin. I'm about to go to chapter 2, where he introduces metric spaces. So here he's defining metric spaces, set with a distance function. I'm just kind of scrolling through to try to jog your memory here. He defines the notion of, he calls it a neighborhood, but that's kind of outdated use of that terminology. Now we call this the open ball centered at P of radius R. And we use these to define what is an open set. And here it is. Unfortunately, it's part F of definition 2.18, so it doesn't look as important as it really is, but it is very important. A set is open if and only if every one of its points is an interior point. In other words, every one of its points has a neighborhood, where by neighborhood he means open ball, centered at that point, which is fully contained in the set. So that's our definition of open from earlier. Of course, you already know this. I'm just reminding you for the moment, since it's starting to become important again. And you see where the metric comes in is in defining what is meant by what Rudin calls neighborhood, what we're calling open ball. To define what this means, you need to use the distance function. Okay, so the main reason I'm showing you this is so I can go back and remind you about something. Oh yeah, well this is good to remember. Every ball, by this he means ball, every open ball is an open set, no matter what the metric is. Yeah, open if and only if complement is closed. And where is it? Ah, here it is. So this is what I want to show you. If you have one metric space sitting inside another metric space, then you end up with well, okay, so if you have a subset of a metric space, then the subset gains a metric, right? The metric you get by restricting the metric from the larger space to the subset. So a subset of a metric space is very naturally a metric space. Okay, so in the y subset x situation, y and x are both metric spaces. That means if you have a subset E of y, then there are two possible meanings for what you might mean when you say, there are two possible things you might mean when you say E is open. You could mean E is open as a subset of x, so using x-type balls to define what interior means, or you could mean E is open as a subset of y, using y-type balls to define what interior means. And the x-type balls and the y-type balls could be different, since the y metric is a restriction of the x metric. So we have this theorem that relates the two concepts. When you're talking about a subset of y being open relative to y, then that's equivalent to being the intersection with y of an open subset of x. Okay, so if this is like old and you've forgotten this idea, then maybe pause the video and soak this in again. And I'm going to go back. I'm going to go back here and continue. Sorry, so that will be relevant in a moment. So we're still in definition. We're still writing this definition. X, any metric space. This, the collection of open subsets. Then we define the Borel sigma algebra. On X to B. And here's the notation for it. We're going to write script B of X. And it's defined to be the sigma algebra on X generated by the open subsets, so generated by this set. So I know this sometimes looks a little bit like a J, but it's a T. It's a script T. So if you use the word measurable to describe the idea of being in a sigma algebra, then the Borel sigma algebra on X is the one generated by the declaration that all open sets are measurable. So if you say all open sets are measurable sets, and then now extend that concept of measurability in the sigma algebra sense, so include whatever else you need to include as measurable in order to make that collection a sigma algebra, then what you get is called the Borel sigma algebra on X. So the elements of the Borel sigma algebra are called Borel sets. So elements here are called Borel sets or Borel measurable sets. So for example, you can do this for Rn. Then you would have a notion of Borel subsets of Rn. Now, you probably by now have a nice intuitive picture of what is an open subset of Rn. It's like a subset of Rn where if you take any point, then it's really deep enough inside that you can wiggle around a little bit and stay inside, right? Some kind of intuitive picture like that. Open subsets of Rn are intuitively describable things. Borel subsets, well, there's a lot of them. It's hard to think of a not Borel subset, actually. So, for one thing, when you create a sigma algebra out of the open sets, when you create a sigma algebra, you're including, you need to make it close under complements, right? So you immediately need to also include the complements of the open sets, which are also the closed sets. So it would have an equivalent here to define the Borel sigma algebra to be the one generated by closed rather than open subsets. Then you're including all the countable unions, countable intersections, and countable unions of those, and countable intersections of those, and so on and so on. And we saw in the last video, or in the previous lecture, that even if you do that forever, that's still not necessarily enough to describe the full, everything that's here, to describe the full sigma algebra generated by a set. So this is kind of a funky construction, I think. All right, so after we do this, let's suppose that E is a subset of X. Well, let me put it this way. Suppose X is a metric space and E is a subset of X. So I'm leaving out the notation. Sometimes we say this, right? X comma D with a metric function. I'm sort of leaving that out, since all I care about from the metric space is this collection of open subsets. So let this be the collection of open subsets of X. Then, remember I was just saying, if you have a subset of a metric space, then you can restrict the metric to it, and then it's itself a metric space, right? So there is such a thing as the collection of, let's call it T sub E. There's such a thing as the collection of open subsets of E. Now we saw in this theorem back here, from the good old Rudin days, that, so here I have E, a subset of X, so I changed the notation a little bit. We saw that the collection of open subsets of E is not just, so what one might naively think is that it's just take the open subsets of X that are also subsets of E. No, it's not that. It's take the open subsets of X and intersect them with E. So this is an example of this relative topology or subspace topology idea. Now, by our definitions, by the definition of the Borel sigma algebras, by the definition of the idea of Borel sigma algebra, the Borel sigma algebra on X and the Borel sigma algebra on E are defined to be, respectively, the sigma algebra on X generated by the topology on X, and sigma algebra on E generated by the topology on E. Now here's another nice way that you might try to describe the Borel sigma algebra on E. So the Borel subsets of E, you could say, are the ones you get when you take Borel subsets of X and intersect them with E. Just like the open subsets of E are the ones you get when you intersect open subsets of X with E. So there's this other thing that you might like to refer to as this, but it's not clear that it's the same thing. So what about if I take the collection of, let me use B for Borel set. This is a Roman B, not a script B. So what about if I take the intersections of the Borel subsets of X with E? So take the Borel subsets of X, intersect them with E. So what about this? Is it the same as, so is this collection of sets the same as the Borel subsets of E? And yes, and now we have a really easy way to argue that it is. So I'm going to leverage all the work that we did in the previous few videos with that Lorillary, what I called, about pulling back and pushing forward sigma algebras. So what's going on here, when I intersect things with E, that's like pulling them back under an inclusion map. So when I say yes colon, that means I'm about to explain why. Why yes. So first, let's use I to denote the inclusion from E into X. meaning it's the identity map. It's just I'm thinking of X as the codomain. So then taking a preimage of a set under I, taking a preimage of a subset of X under the function I, that's the same as intersecting with E. So G intersect E up here, which my face is covering part of. So let me just copy this. So then this we can describe like this. G intersect E is I preimage G. And also, this thing is actually just, we're just taking the preimages of all the Borel measurable subsets of X. Okay, so what is this then? If you take the preimages of all the elements of a sigma algebra under a map, that's what we call the pullback. This is the pullback under the inclusion map of the Borel sigma algebra on X. So the question that I'm asking here when I say are these the same is the Borel sigma algebra on E what I would get if I pulled back the Borel sigma algebra on X along the inclusion? Now the Borel sigma algebra on E is the sigma algebra on E generated by the topology on E, right? Which I have just described like this. The collection of preimages of all the open subsets of X under the inclusion map. So is this the sigma algebra generated by the pullback of the topology the same as the pullback of the sigma algebra generated by the topology? Yes, that is what we showed way back here. That was this idea here. So this thing that I just wrote down is indeed the same as this. All right, so there you have the definition of the Borel sigma algebra on a set, and a nice result about what happens when you have a subset of a metric space. So this works for any metric space, including subspaces of metric spaces. And if there's one thing you're going to watch out for here when you look at subspaces, is it's similar to what happened with the notion of open set. So like the collection of open subsets of E, where E is a subset of X, the collection of open subsets of E is not a subset of the collection of open subsets of X. So we do not have this with the notation that I had set up here. We do not have that. Open subsets of E are not necessarily open subsets of X. Unless E itself is open, then you have that. Similarly, you do not have that Borel subsets of E are Borel subsets of X. You do not have that. Unless E itself you know to be Borel, then yeah, when you intersect Borel subsets of X if you intersect two Borel sets, you get a Borel set. So then it works, but in general you wouldn't have that.